occupied France, August 1943. The call came just after 16 hours to Oberleutnant Werner Schultz, Chief Technical Officer of Jagdgeschwader. An American P-47 Thunderbolt had crash-landed nearby, pilot captured, aircraft mostly intact. For Schultz, this wasn't just another downed enemy plane. It was a chance to solve a mystery that had been haunting Luftwaffe intelligence for months. German pilots kept returning with impossible stories about this massive American fighter. Now Schultz would see for himself. When he arrived at the airfield and laid eyes on the P-47, his first reaction mirrored every German pilot's assessment. This thing looked absurd. Grotesque even. Built around an enormous radial engine, it weighed nearly 8 tons, fully loaded, double the weight of Germany's frontline WWII fighter. German pilots had nicknamed it the Flying Milk Bottle, and standing there on the tarmac, Schultz understood why. It looked like it had no business being airborne. But Werner Schultz was a scientist, not a combat pilot. He didn't care what it looked like. He cared what it could do. And as he began his methodical examination, what he discovered would shake him to his core, not just about the aircraft, but about the war itself. Schultz started where any engineer would, with the heart of the machine. When his team removed the cowling from the Pratt Whitney R-2800 double wasp, they stood in stunned silence. 18 cylinders arranged in 2 rows of 9, creating the radial configuration that explained the P-47's bulk. But size wasn't what stopped them cold, it was the precision, the quality, the sophistication. Every component was machined to tolerances that German factories were struggling to maintain under the pressures of war. The cylinders were perfectly uniform and balanced. The crankshaft was a masterpiece of metallurgy. Schultz pulled out his notebook and ran the calculations. Based on displacement and design, this engine produced at least 2,000 horsepower, possibly more with the turbocharger system. For comparison, the BMW 801 radial and the FW190 generated about 1,700 horsepower at maximum output, and that was pushing German engine technology to its absolute limits. The Americans were mass-producing engines with 20–30% more power, and doing it with apparent ease. But what truly disturbed Schultz was what he didn't find. He examined the engine for the kinds of compromises German factories were increasingly forced to make: lower-grade materials, simplified manufacturing, shortcuts to save resources. He found none. This engine was built with high-grade aluminum alloys, precision bearings, and components that showed no evidence of material shortages. It was built the right way, not the expedient way. "Herr Oberleutnant, look at this," one of his mechanics said, pointing to the cylinders. "Each one is individually removable. If damaged, you can replace just that component without disassembling the entire engine." Brilliant design, Schultz thought. Faster repairs, less downtime, more aircraft operational. German engines required extensive disassembly for major repairs. This American design assumed maintenance would happen frequently and needed to be efficient. Then Schultz discovered the P-47's real secret, the turbocharger. He'd read intelligence reports, but seeing it in person was different. A complex network of ducting snaked from the engine through the fuselage to a turbine mounted in the rear. The system used exhaust gases to spin a compressor at over 20,000 RPM, forcing pressurized air back into the engine. The engineering was staggering. Exhaust ducting had to withstand extreme heat. The turbine had to spin at speeds that would tear apart inferior bearings. The entire system required precise calibration to avoid destroying the engine. German engineers had experimented with turbochargers, but never successfully fielded one. The technical challenges were too great, the materials too difficult to source, the manufacturing too complex. Yet here it was in an American fighter being mass-produced. Not a prototype. Not an experimental aircraft. A production model. One of hundreds, perhaps thousands. Schultz ran the calculations. With this turbocharger, the P-47 could maintain full power at altitudes where German fighters were suffocating. Above 25,000 feet, The FW-190 and BF-109 lost significant performance as their mechanical superchargers struggled in thin air. The P-47 would be hitting its stride fast, powerful, completely dominant in the high-altitude realm where German fighters had to intercept bomber formations. "Can we replicate this system, Herr Oberleutnant?" his assistant asked. Schultz shook his head slowly. "Not with our current manufacturing capacity. This requires precision machining, high-grade steel alloys, thousands of man-hours of skilled labor. We're already struggling to produce enough basic aircraft. Adding this level of complexity." He paused. "It's beyond our capabilities." The realization was crushing. The Americans hadn't just built a better fighter. They'd built a fighter that represented a level of industrial sophistication Germany couldn't match. After the engine, Schultz turned his attention to the airframe. What he found was equally disturbing. The P-47 had taken significant battle damage cannon shells through the fuselage, machine gun fire riddling the wings. Yet it had flown back and made a controlled landing. Schultz examined the damage patterns. Multiple 20 cannon hits, the kind that would typically shred a German fighter. But the P-47 structure had absorbed the punishment. Heavy-gauge aluminum skin, robust internal framing, redundant control systems, all contributing to incredible durability. He pulled damage reports from Luftwaffe units. Time and again, pilots reported pumping cannon fire into P-47s only to watch in disbelief as the American fighters continued flying. The reason was clear: where German fighters optimized for weight savings and agility, the P-47 was designed to absorb punishment and keep flying. The cockpit armor was extensive thick steel plates protecting the pilot from multiple angles. But most importantly, that massive R-2800 radial engine served as a shield. Unlike the liquid-cooled inline engines in German fighters, the radial had no vulnerable coolant system. You could shoot cylinders off the engine, and it would keep running. Documentation showed P-47s returning to base with multiple cylinders destroyed, fuel tanks punctured, control surfaces shot away. German fighters with similar damage would have fallen from the sky. "It's over-engineered," one of his engineers observed. "They've added weight for durability that could have been used for performance." "Yes," Schultz nodded. "But they can afford to. They have engines powerful enough to carry the extra weight. We don't. We have to optimize for weight because we lack the engine power to overcome it." It was a fundamental difference in design philosophy, and brutally, the American approach was working better. Schultz examined the armament next: 8 Browning M2.50 caliber machine guns, 4 in each wing. His heart sank as he calculated the implications. Each gun had approximately 400 rounds. Total ammunition, 3,200 rounds. Combined rate of fire, over 100 rounds per second. A 1-second burst would put 100 heavy slugs into a target. A typical 2-second firing pass would launch 200 rounds. German fighters typically carried 2 or 4 machine guns plus 1 or 2 cannon. Total firepower was less and ammunition more limited. A Bf-109 might have 60 rounds for its cannon, 500 for its machine guns. Once expended, the pilot returned to base. The P-47 pilot could fire almost continuously for 30 seconds, multiple long bursts across several engagements. Schultz examined the .50 caliber rounds themselves. Heavy, high-velocity projectiles that could punch through armor and structural components with ease. He'd read pilot reports describing P-47 fire as a wall of lead. Now he understood why. With 8 guns converging at a focal point, anything caught in that cone of fire would be shredded. German aircraft with their lightweight construction and limited armor would disintegrate. As Schultz compiled his technical report, he began seeing a pattern that transcended any single component. Every system on the P-47 spoke to an underlying industrial capacity that was staggering. The engine required precision machining and high-grade alloys. The turbocharger required advanced metallurgy. The airframe required massive amounts of aluminum. The armament required a functioning ammunition production industry. Any one of these would strain German industry. The P-47 had all of them, integrated into a single aircraft being mass-produced. Schultz requested production data from intelligence sources. What he learned was soul-crushing. Republic Aviation was building P-47s at a rate of over 500 per month by late 1943, with plans to ramp up to 600, 700, even 800 per month by 1944. German factories struggled to produce 300-400 single-engine fighters per month total across all types, and German production was constantly disrupted by Allied bombing. But the numbers got worse. The R-2800 engine wasn't exclusive to the P-47. It powered multiple American aircraft. Total production would exceed 125,000 units during the war. Germany's entire production of aircraft engines for all types, across the entire war, would be roughly 250,000 units, most significantly less powerful. The Americans were building more of a single advanced engine type than Germany could produce total engines. Schultz sat at his desk, staring at the numbers. He ran the calculations again, certain he'd made an error. The numbers didn't change. American aircraft production for 1943 was projected to exceed 85,000 aircraft. German production, about 25,000. A ratio of more than 3:1. But it was worse than that, because American aircraft were on average heavier and more complex. A single B-17 bomber required more aluminum and man-hours than 3 Bf-109 fighters. The Americans were building thousands of B-17s. America was fighting a global war, supplying the Soviets with thousands of aircraft and tanks, equipping British forces, and still outproducing Germany in every category. Schultz's final report was due for High Command in Berlin. As he compiled his findings, he knew he was writing something dangerous. The report documented the P-47's technical superiority. It acknowledged Germany lacked the industrial capacity to produce equivalent systems. And it contained a conclusion that would be seen as defeatist. The P-47 Thunderbolt represents a level of industrial and technological sophistication that exceeds Germany's current capabilities. Its widespread deployment suggests American production capacity far exceeds previous intelligence estimates. Recommendation: tactical adjustments to minimize engagement with P-47 at high altitude. Strategic assessment: continued attrition against numerically and technically superior enemy aircraft will result in unsustainable losses. In other words, we can't beat this. If we keep fighting the same way, we'll be destroyed. Schultz's commanding officer read the report and looked at him with respect and concern. You know this will not be well received in Berlin. They don't want to hear that American aircraft are superior. Should I alter the findings? Schultz asked, already knowing the answer. No. The report is accurate. But prepare yourself, the leadership doesn't respond well to uncomfortable truths. The report was forwarded up the chain. Schultz never received an official response, but heard through informal channels that it had been dismissed as overly pessimistic. One staff officer reportedly said, "This engineer has been demoralized by enemy propaganda. The P-47 is crude American engineering, inferior to our designs." Schultz wasn't surprised. He'd seen this pattern before. Intelligence that contradicted Nazi ideology was rejected regardless of accuracy. In the months following his report, Schultz watched his predictions come true. P-47s appeared in increasing numbers over Europe. German fighter losses mounted. Experienced pilots were shot down and not replaced. The tactical recommendations he'd made were slowly adopted, but by then it was too late. The Americans had achieved air superiority through sheer weight of numbers and technical advantage. Schultz examined other captured American aircraft. Each told the same story: superior materials, sophisticated systems, evidence of an industrial base operating at a scale Germany couldn't match. A captured C-47 transport, one of over 10,000 that would be produced. Germany's entire transport fleet was a few hundred aircraft, mostly obsolete designs. A P-51 Mustang combining the P-47's range with even better performance. Its engine was a Packard-built Rolls-Royce Merlin, produced under license in America. Thousands of them. Every aircraft reinforced the same conclusion: Germany was losing an industrial war to an enemy with overwhelming material superiority. What haunted Schultz was that this information was available. The intelligence existed. German agents reported on American production. Captured equipment proved the quality. But the leadership refused to accept it, or more accurately, believed that German will and superior tactics could overcome material disadvantage. Schultz had been trained as an engineer. He believed in numbers, in mathematics, in physical reality. And the physical reality was undeniable. Germany was being buried under an avalanche of American steel. After the war, when production figures were declassified, Schultz's estimates were proven conservative. He'd actually underestimated American capacity. Total American aircraft production from 1941,945, over 300,000 aircraft. German production in the same period, approximately 94,000. The United States produced over 15,600 P-47 Thunderbolts alone, more than Germany produced Bf-109s and FW-190s combined. That are 2,800 engines Schultz examined with such awe in 1943. Over 125,000 were built not just by Pratt Whitney, but by Ford, Chevrolet, and other automotive companies converted to war production. The industrial mobilization that produced these numbers was unprecedented in human history. American factories that had been making cars were retooled to make aircraft engines. Shipyards that built freighters were building aircraft carriers. And it wasn't just quantity, the quality remained high. Late-war American aircraft showed no signs of declining standards, no shortcuts, no compromises forced by material shortages. German aircraft, by contrast, showed increasing evidence of resource constraints, lower-grade materials, simplified construction, quality control issues as experienced workers were drafted and replaced by forced labor. Schultz survived the war and was interrogated by American technical intelligence officers. They were particularly interested in his 1943 report on the P-47. Did you really conclude from examining one aircraft that Germany would lose the war? An American officer asked. Schultz thought for a moment. I concluded that Germany could not win an industrial war against America. The P-47 was evidence of a production capacity we couldn't match. Every component, every system required resources and manufacturing capability that exceeded Germany's total capacity. But you were just one engineer. Surely others reached the same conclusion. Many did. But in the Third Reich, stating inconvenient truths was dangerous. Better to remain silent than be accused of defeatism. The American officer nodded. We found your report and captured German files. It was marked filed, no action required. Did that surprise you? Schultz laughed bitterly. No. I expected it. The Nazi leadership didn't want intelligence. They wanted validation of what they already believed. When reality contradicted ideology, reality was dismissed. The story of Werner Schultz and the captured P-47 is a microcosm of Germany's strategic failure. A trained engineer examined enemy equipment, reached an accurate conclusion about Germany's industrial disadvantage, and was ignored. His experience paralleled that of Admiral Canaris, who warned about American industrial capacity. Albert Speer, who knew Germany couldn't win a production war. Adolf Galland, who recognized the P-47's tactical superiority. Sepp Dietrich, who knew the Ardennes offensive would fail for lack of fuel. In every case, competent men saw the truth and were trapped in a system where truth was subordinate to ideology. They provided accurate assessments and were dismissed as defeatists or pessimists. The Nazi regime was built on the premise that German racial and cultural superiority would overcome any material disadvantage. That will and determination mattered more than industrial capacity. That ideology could defeat mathematics. They were wrong. And men like Schultz knew they were wrong from the moment they examined the evidence. But knowing the truth and being able to act on it are different things. Schultz's report on the P-47 should have been a wake-up call. It should have triggered a fundamental reassessment of Germany's strategic position. Instead, it was filed away and forgotten. The P-47 went on to become one of the most produced fighters of World War II. Over 15,600 were built. They destroyed thousands of German aircraft. They supported the invasion of Europe. They helped achieve the air superiority that made Germany's defeat inevitable. And it all started with one engineer examining one captured aircraft and realizing that his nation had already lost a war they didn't know they were fighting. Not a war of soldiers or tactics, but a war of factories and resources. A war where the side with more oil, more aluminum, more steel, and more industrial capacity would inevitably win. America had all of those things in abundance. Germany had none of them. The P-47 wasn't just an aircraft. It was a mathematical proof written in aluminum, steel, and high-grade alloys that the outcome was already determined. Schultz saw it clearly in August 1943. The war would continue for another 20 months, consuming millions more lives. But the ending was already written in the specifications of that grotesque, ungainly flying milk bottle sitting on a French airfield. The numbers don't lie. They never do.